Thank you so much for your kind introduction. So you see a lot of logo on this first slide because yes, I am responsible of innovation for Institut d'Optique in France. But we have also some specific initiative for Nouvelle-Aquitaine, which is a hub around the quantum technology, which is called NACIDI Center. We work, for example, with Toptica, with Excel, etc., which are located in Nouvelle-Aquitaine. And as IOJS, we are also in charge of a special governmental plan for securing lasers in France with this European partner. For example, we also work with Toptica on this subject, and this is the program Atom Control, which you can see the logo of this program, which was launched 1 month ago, and which is 15 millions for lasers in France during 5 years. But today, what I want to emphasize is that there are many technologies which are involved in quantum, and photonics are nearly everywhere in quantum computing. So statement is that optics and photonics are, of course, core technologies of quantum since the beginning of these technologies. And we do believe, especially in Nouvelle-Aquitaine, where we have a lot of people involved in lasers and fibers, etc., that quantum technology presents various innovation opportunities for the optics and photonics community. So there is still a gap between the laboratory and the market, but the photonics ecosystem has a true key plan to build this ecosystem. So the questions I'm going to try to answer is, who could be the key players, what is the reality of this quantum market, and how to build together a perennial photonics market. So we are going to speak all this afternoon of quantum computing. So very briefly, I will report of what is the interest of quantum computing, our classing of problems which are exponentially difficult to deal with. For example, the famous Shor factorization of algorithm, and there is a considerable potential applications of this new technology of replacing bits by qubits, for example, in material science, condensed matter, protected communication, etc., optimization problem in pharmacology, the traveling salesman, etc., and the power of the quantum computer comes from entanglements, but in weakness from the fragility of superposition. So depending of the technologies that you are going to use, for example, so you know these technologies, there are atoms, there are ions, superconducting, hybrid, molecular color center, photonics. We all love photonics, so maybe it will be our preferred. I'm going to speak about this. And to do these quantum computers, we need some key enabling technology where you can find cryo, control electronics, but also photonics. First of all, we do like photons. So building a computer with photons, it was a dream less than 1 decade ago, and it begins real. So we have the pleasure to have our colleagues from QUICS today. So Quandela in France, QUICS also. And there are many ways to produce these photons and to detect them. One of them, of course, is quantum dot technologies, which is developed by C2N or Quandela, but also SPDC, which is used for other technologies. So for these solutions, quantum computing with photons, you need single photon sources, single photon detectors, and photonic integrated circuits. But there are also quantum computing with atoms. We have champions, I think, in France with Pascal. So this is based with the use of neutral atoms as qubits. The particularity of this technology is that this is not really computing, because for the moment it's difficult to implementize some algorithm on this, but we are more or less on simulations. This means that you need to pick up some neutral atoms like rubidium, cesium, or strontium, etc., ytterbium for other competitors, and to manipulate it with lasers, very low noise lasers, and to simulate quantum algorithm with this kind of lasers. So this is clear that with this technology, lasers and special modulation bricks are very essentials for this quantum computing platform. But this is also the case, for example, for ions. In this really nice publication, so 2021, you can see an ion which is floating through lab on chip with fiber optics. So for manipulating these neutral atoms or ions, you need a lot of lasers. And for example, in this very nice photography, you can see that you have lasers, but they are linked with fibers. So I think that we have to work on integration, photonic integration, but also coupling with fibers. So this is the case for atoms, this is the case for photons, but this is also the case for ions. And what is special with these platforms, which are ions or atoms, is that you don't choose if you need I don't know, 1 micron or 2 micron. No, this is the nature who decides what you need, and the nature didn't decide that every atoms work at the telecom wavelength. So you have to develop special wavelengths with extreme stability, agility, tunability. So there is a lot of work on lasers to do for these particular platforms. And this is surprising, but it is also the case for example, with supraconductor. In this example, you know that for example, Google or IBM work with this oldest technology, with this supraconductor, and to support the RF on the bus of this on the qubit, you can use photonic link and impress the number of qubits which can be read on a superconducting qubit using a photonic link. So you need also on supraconductor some photonics. And of course, if one day we manage to have some quantum computer which work very well, we can dream of quantum internet, and then we'll have to work on nodes and some to make speak two computers together with fibers, but also with intermediate nodes such as quantum memories, for examples. So some requirements for near-term technologies for photonics on lasers. So we have to work on power, wavelength range, no noise, etc. Swap requirements on lasers. We have to work on our sovereignty for components in free space, but also fiber, crystal, diodes, etc., etc. We have to work on advanced optical detectors, higher efficiency telecom detectors, but not only at telecom wavelengths, as I mentioned before. We need larger detectors for space, for examples. Integrated photonics will play a key this will be a key enabling technology in the future to miniaturize these computers with new production facilities, cryogeny compatibilities, loss reduction, source detector, etc., etc. And of course, on the longer term, I do believe that we have to work on single photon sources and detectors. Of course, if we must deploy it as computers from today, we have to work on the cost reduction and also to sync foundry fabrications for integrated photonics. I would like to mention that since October 23, quantum technology is considered as dual use. So this can be for our colleagues from photonics a problem, because we think that there is not a fundamental lack of supplies, because Europe is the home of the best suited lasers or photonics. This is what we believe. And we serve maybe 60 or 80% of the current global market. But there can be a fundamental discrepancy between expectations of quantum customers and swap requirements, of course, and maybe a lack of realism on the market size. And today we must mastering with a small volume today by testing the quality in limited series and maybe preparing a ramp up. And we need non-European markets. Capital investment is needed, not only from government, but we need to increase these implications through European contracts. Thank you. It was what I wanted to say. Yeah.
Okay, thank you very much, Johan. That's a very nice summary.